Today, we are diving deep into the heart of the atom to unravel a really fascinating paradox. It's the source of the most powerful energy in the entire universe. And it all comes from something that's, well, missing. It's a story about missing mass, cosmic glue, and the very engine that makes stars shine. So here's our game plan. We're going to start with a really puzzling mystery right at the center of the nucleus. Then we'll uncover the solution with an equation you've definitely seen before. We'll see how that solution literally holds the universe together, and then we'll put all that cool theory into practice with some actual calculations. All right, our journey kicks off with a question that seems like it should have a super obvious answer. But, the world of nuclear physics is packed with surprises that totally flip our everyday intuition on its head. Just think about it for a second. If you took a car apart, piece by piece, and you weighed every single component, the engine, the doors, the nuts and bolts, everything, shouldn't the total weight of all those parts add up to the weight of the fully assembled car? For everyday things like this Lego model, the answer is a simple yes. The sum of the parts is the same as the mass of the whole. Right? No surprises there. That's just how we expect the world to work. But, and this is a big but, when we zoom all the way down to the atomic nucleus, something really bizarre happens. If we take the individual parts of a helium nucleus, that's 2 protons and 2 neutrons, and we add up their masses, we get a total that's actually heavier than the measured mass of the helium nucleus itself. The parts literally weigh more than the whole. How weird is that? Now, this missing mass isn't just a measurement error. It's a real observable thing. And physicists have a name for it, the mass defect. And it's the absolute key that unlocks this entire puzzle and leads us to a source of unbelievable power. Okay, so this begs the question, where in the world did that mass go? It didn't just poof, disappear. The answer comes from what is probably the single most famous equation in all of science, a formula that completely revolutionized how we see the universe. And this is where the genius of Albert Einstein comes into play. You see, the mass wasn't lost at all. His legendary equation shows us that mass and energy are really just two sides of the same coin. That mass defect was converted into a staggering amount of energy. So this energy, born from that tiny bit of missing mass, doesn't just fly off into space. Nope. It has a very special name and an incredibly important job to do inside the atom. It's called the binding energy, and you can think of it as the ultimate cosmic glue. It's the energy that got released when all those protons and neutrons first came together. And now it's the very force that holds the nucleus together, fighting against the insane repulsive force of all those positive protons trying to fly apart. So the bigger the mass defect, the stronger the binding energy, and the more stable the nucleus is. And this powerful idea of binding energy, well, it doesn't just apply to one atom. It governs the stability of every single element. And get this, it's the engine that has been powering the stars for billions of years. Now, this graph is one of the most important charts in all of nuclear physics. Don't worry about all the text, just focus on the shape of the curve with me. Along the bottom, you have the number of particles in a nucleus, and going up the side, you have the binding energy per particle, which is basically a stability score. Understanding this curve is everything. As we go from the really light elements like hydrogen, the curve shoots up, which means the nuclei are getting way more stable. It hits this peak right around iron 56, making it the most stable, most tightly bound nucleus in the universe. Then, for all the heavier elements, like uranium, the curve starts to slope back down, meaning those nuclei are getting less stable again. So this natural drive to be more stable, to get closer to that peak, gives us the two most powerful nuclear processes there are. The really heavy guys on the right side of the peak, like uranium, can split apart into lighter, more stable pieces. That's fission. And the really light elements on the left, like hydrogen, can slam together to form heavier, more stable elements. That's fusion. And that's exactly what's happening in the core of our sun, releasing a mind-boggling amount of energy. Okay, the theory is awesome, but let's make it real. Let's actually walk through how physicists can calculate these incredible energies, all from a tiny little defect in mass. Let's start with carbon-14. Now, don't scramble to write down all these numbers, just follow the story. First, we add up the mass of what carbon-14 is made of, 6 protons and 8 neutrons. Then we subtract the mass that we've actually measured in a lab. That tiny little difference is our mass defect, the missing mass. The last step is the E equals mc squared magic. We convert that mass into energy. Using a handy conversion, we find that that tiny speck of mass is equivalent to 102 mega-electron volts of binding energy. Now let's do the same thing with a real heavyweight, uranium-238. Same process, just bigger numbers. The total binding energy is huge, over 1800 MeV. But here's the important part. To really compare stability, we have to look at the energy per nucleon. For uranium, it's 7.6 MeV. Now that sounds like a lot, but remember our graph. Iron, at the peak of stability, is even higher. So even with all that energy, uranium-238 is actually less tightly bound together per particle, which is exactly why it's a good candidate for fission. And this is where we see the raw power. Check out this fission reaction. Before the split, we have a uranium-235 nucleus and a neutron about to hit it. We add up their mass. Then after it splits, we have the leftover pieces, barium, krypton, and 3 new neutrons. We add up their mass. And look at that. The products weigh less than what we started with. That mass didn't just disappear. It was instantly converted into a 260 MeV burst of pure energy from a single atom splitting. That is the incredible power of the mass defect. Okay, you've seen the process in action. Let's run through one more example together, this time with nitrogen-14, just to really lock in the concept from start to finish. So, nitrogen-14. We know it has 7 protons and 7 neutrons. Just like before, step 1 is to calculate what its mass should be if you just added up all the parts. Then, we subtract what its mass actually is. That difference right there, that's our mass defect. It's the starting point for everything else. Now, we take that mass defect and we turn it into energy. We'll use the slightly more precise conversion factor here, multiply it out, and we get a total binding energy of 101 MeV. And for our final stability score, we just divide by the 14 nucleons, which gives us 7.2 MeV per nucleon, placing it right on that nice stable part of the curve we saw earlier. All right, let's step back from the numbers for a second and lock in the big ideas. Think about it. Could you explain what the mass defect is and how it's connected to binding energy and how that binding energy explains the power of both fission and fusion? It's really all one connected, beautiful story. So let's wrap it all up. It all starts with the mass defect, that little bit of missing mass when a nucleus is built. That mass isn't gone, it's just been transformed into binding energy, the cosmic glue holding it all together. The stability of any element is measured by its binding energy per particle. And finally, fission and fusion are just nature's way of shuffling atoms around to get to a more stable state, releasing an enormous amount of energy along the way. Which leaves us with a final thought. We started with a simple question about weight and ended up discovering that a tiny little imperfection, a defect in mass, is the source of the most powerful energies we know. It just makes you wonder, right? What other profound secrets of the universe are hiding, not in the obvious things, but in the subtle little paradoxes, just waiting for us to find them? Thanks for watching.